Good afternoon, class. Today I have the pleasure of sharing the results of over 100,000 Mystic Forges of exotic weapons. This data is genuinely exciting and presents a great opportunity to cover some statistical principles while explaining my findings and conclusions. This isn't a full-blown statistics lecture. I will give an overview of some topics, but if you're unsure about a term I used or want to learn more, leave a comment and then copy that comment and paste it into ChatGPT. Let's talk about the data set first. About 3 years ago, we announced the Kickstarter model for funding the collection of precursor forging data. The plan was simple. We slowly buy-ordered 8,000 exotic weapons of each weapon type, excluding underwater weapons, totaled the cost, and opened a funding round. We split the cost into shares, allowing members of the community to buy into the project. After funding, we collected data on 2,500 forges, reforging the outputs as necessary. Then, we tallied the value of the outcomes and paid out a proportional percentage to each share, as well as sharing a link to the data sheet containing the results. Committing to large samples of predetermined size made this data extremely resistant to sampling and reporting bias, which are both unfortunately quite common in the Guild Wars 2 community. The rest of the data comes from personal data collection efforts by those of us who hosted Kickstarter and a few other well-respected data gurus. I've created 2 spreadsheets, one with only Kickstarter data and the other containing all 100,000. Head down to the description to check those out, and while you're down there, can you say hi to the like and subscribe buttons for me? They stopped answering my calls and I hope they're doing okay. Now let's start dissecting this data. One question we wanted to answer is if each weapon type had the same chance to produce a precursor. Here are the counts of each precursor we got from 2,500 forges. Our lowest count is 14 sparks, and our highest count is double that at 28 howls. When you have double the drop rate at a massive sample size like this, surely there's a difference, right? Well, it's quite a range, but how can we tell if this is just the result of normal variance? Since these counts are all from samples of 2,500 forges, we have what is called a sample distribution. According to the central limit theorem, sample distributions will approach a normal distribution as the sample size increases. After we define the curve by calculating the mean and standard deviation, we can observe that all of our results fall comfortably within 2 standard deviations. This suggests that our results are within normal variance for this sample size. In other words, it is likely that they have the same drop rate for every weapon type. 2 of these precursors are special though. Dusk and Dawn both come from the Greatsword forges, which is why we forged twice as many for Kickstarter, and in the combined set, we have over 16,000 Greatsword forges. We wanted to know if the drop rate for getting a Greatsword precursor was different, and whether Dawn or Dusk was more common than the other. We accounted for 157 Greatsword precursor results, 83 Dusk, and 74 Dawn. We can use the Binomial Distribution formula to calculate how likely this result would be for a true 50-50 split. A two-tailed calculation gives us a p-value of 0.52. This tells us that our result is very normal, assuming there's a 50-50 split. While we were reviewing the data on all of the other weapons, we noticed something interesting. I think the best way to show this is a histogram of the drop rate percentage of each non-precursor weapon within their samples. Would you look at that? The curvaceous swells of bell curves, the hidden memories in our histogram queries, lovely, magnificent mounds of local maxima within bounds. Makes me want to just reach out and separate them into normally distributed datasets. And we can do that as long as we support it with the right evidence. Specifically, we can try to find an independent variable that could explain this distribution, and that variable is weapon level. When we split the dataset between level 80 weapons and sub 80 weapons, the histogram is cleanly separated. That all makes sense intuitively, but it's not very mathematical. We can be a little more objective by performing what is called a chi-squared goodness of fit calculation. This part of the video has the most statistics jargon, but if you followed along so far without your eyes glazing over, you'll be fine. For demonstration purposes, let's look at the data for axes. We'll pose 3 hypotheses. 1. All weapons have the same drop rate. 2. All level 80 weapons have the same drop rate. And 3. All sub 80 weapons have the same drop rate. The next thing we need to decide is how confident we want to be in our results. We do this by specifying an error rate, or alpha, to compare against our tests. I usually use an alpha of 0.05, which roughly means I'm 95% confident in my test results. If the chi-squared calculation gives us a p-value that is below the alpha, we can reject the hypothesis with that level of confidence. For axes, we see that the p-value for hypothesis 1 is basically 0, and the others are above 0.05, so we would reject 1 and not reject 2 and 3. However, this gets a bit tricky when we do this test for every weapon. Looking at these tests on all weapons, hypothesis 1 is soundly rejected, but we have a few p-values threatening to reject 2 and 3 for our alpha. There is an explanation for this. When you do a series of similar tests, you increase the chance of getting a false positive, which is called family-wise error rate. There are a lot of ways to correct for this, the simplest of which, Bonferroni correction, involves multiplying your p-values by the number of tests. In our case, that means multiplying by 16, which brings everything above board. Now, multiplying by 16 is a big correction, and the results of our tests don't mean our hypothesis is correct, only that the data doesn't give us enough confidence to reject it. We can always do a test with more data, but before I do, I want to quickly mention a dangerous type of bias called p-hacking. This relies in part on repeating tests until you get a desired result. It's important to report on the full picture and not filter out data or tests to make a conclusion appear more decisive or more interesting. Here we're going to look at Enko's data. He has a similar or greater sample size for 11 of the weapons, so we'll repeat the chi-square on those. We have one p-value below our alpha, but it goes away quickly with Bonferroni correction. Reviewing our results as a whole, the most reasonable conclusion is that level 80 and sub 80 weapons have different drop rates, but any further differences within those subgroups are undetectable or non-existent. And to finish things out, let's take a look at profit calculations, the part you've probably been waiting for. And we could obviously just calculate with the exact drop rate for every weapon we observed, but it's probably more accurate if we normalize the drop rates based on our previously established conclusions. Let's use the average drop rates of precursor, level 80, and sub 80 weapons, then calculate their average value in each weapon type. Multiplying these together gives us the average value of forging each weapon type. Prices fluctuate all the time, of course, so use the spreadsheet in the description to get an updated calculation. Looking at today's prices, however, the outlook isn't good. Ever since the Wizard's Vault started giving out free precursors, the value of these have tanked hard. The average value returned is currently lower than salvaging for Ecto for all except greatswords, and only just barely. You might think this is a disappointing conclusion to such a large project, but that's a short-sighted response. Prices change, and now we have a calculation dialed in. Also, this is just one study, and both past and future studies have led and will lead to profitable ventures as long as we keep looking. Hopefully this video gave you some insight into analyzing data, and perhaps inspired you to tackle your own projects. If so, I'd love to hear about it, so head over to my data Discord where you can talk about it with me and some other like-minded people. That said, thanks for watching, and remember, Gamba bad, it's not gambling if you write it down, and infusions are overpriced garbage.